So if you ever get a question where they ask you to draw a speed time graph, you will be having to find the area under the graph, okay? Please do not try and use a method that we may learn later on this topic for a question where they've asked you to draw the speed time graph or the velocity time graph. The property of the area being equal to the distance is crucial and always makes the problem more simple. It becomes just a problem about shapes rather than a problem about all these complicated formulae that we might be coming up against next, okay? So what we're going to have a look at are some equations which I'm sure you've come across in GCSE, and I know that if you do physics in A-level, you've already looked at some of these equations, which are called the SUVAT equations, okay? I know from the way that they have been taught to students in year 13, people who already have done SUVAT in physics think, oh yeah, I know what I'm doing. And then actually they get a bit confused because some of the ways that they're done in physics, I don't agree with. I think there are some more efficient ways of doing them. So I would ask you just to have your attention sort of switched up to full, even if you think it's something that you already know about, okay? So if you find this page in your booklet, we're going to read through some of this as a bit of a way of me explaining how these formulae, where do they even come from, okay? Where do these formulae even come from? And this is part one, because we're only going to have a look at 2 formulae, probably for today's lesson, and then we'll develop that more when I see you next week. When there is constant acceleration, I've gone on and on about this already, there has to be constant acceleration for this topic. This whole topic is called constant acceleration. Then there is a variety of formulae which relate the following 5 quantities. And you can see why informally we call these the SUVAT, because there are 5 different quantities with those letters corresponding. S is for displacement. How is displacement different to distance? It's in a direction. It is a vector quantity. If I talked about the distance that I travelled from here, and then I walked over to my chair, and then I walked halfway back again, my distance is all the way to the chair and then all the way back again. My displacement, though, is just from where I started to where I finished. So my displacement is actually quite small because I walked back towards myself. It's almost like the displacement is if you took a photograph of me at the beginning, you took a photograph of me at the end. The displacement is just the difference of where I've been stood. It's going to be very, very important that we come across that idea. We've, I think, come across the idea of U being as initial velocity, V as final velocity, A as acceleration, and T is time. And I've drawn here an example of what this might look like for a velocity time graph, okay? You can see that I've put U at the beginning of the graph because that's the speed that it initially has. And that I've got V at the top because that's the final speed that it has over a particular amount of time that has been assigned to it. So I've got an idea of what a velocity time graph looks like. And I've written in our orange box here that it's important you recognize these equations are for a specific interval of time. So that the time t is the duration of the period we're considering, not necessarily the time since the object was moving. So in that example of me walking over to my chair and walking back again, I don't have to say that time is from the very beginning to the very end. I could talk about the period of time from me stood at my chair to the point where I finished up. It doesn't have to be from the beginning of time. It can just be whatever period of time that I want to consider. And it says underneath, each SUVAT equation that we will see involves 4 of the 5 quantities. Typically in a problem, we'll know 3 of the values, the quantities, and we wish to find an unknown 4th quantity. We therefore select the appropriate equation. So there are 5 things, there are 5 equations, and each equation uses 4 of them. So each equation excludes one of those things that is there. Now, you do need to know how to be able to derive these and prove these SUVAT formulae from the graph. So it's important you listen to this bit now, because this is something you could easily be expected to be asked about. Now, we know with a velocity time graph that the acceleration is what property of the graph? The gradient. Okay, so if I wanted to find out what the formula is for the acceleration from this, I can see, using the gradient of the graph, which we know is the acceleration is the change in y divided by the change in x. In other words, how the velocity is changed, v minus u, divided by the change in x, which is the amount of time. So we get v minus u over t, which tells us that the first SUVAT formula, when we rearrange this, if you multiply by t, and then add on u, you get v equals u plus at. That's the first SUVAT formula that will be used quite commonly, okay? The second one is using the second property that we've talked about in speed-time graphs so far. One of them was the gradient. The second thing is the area underneath this graph. We know that the area underneath this graph will be the displacement. So we can see here that this is actually a trapezium. So the displacement, which is the letter S, is the parallel sides, which is U and V. It's the average of the parallel sides multiplied by the gap between those parallel sides, which is T. So our second SUVAT formula is S equals U plus V over 2 multiplied by T. And I've put here for a memorization tip that the formula is effectively still distance equals average speed times time, which is the same as what it was from GCSE. U plus V over 2 is the average speed, whatever it is we're talking about, whether the car we're talking about, or whether someone running. U plus V over 2 is their average, so you've just got speed times time is equal to distance, okay? We're just going to be working with these two formulae to begin with and starting to develop some skills with these. So we're going to just dive straight in with what an example might look like. The first thing you do in these examples is you extract the information from the question and then you think about how you apply them into a formula. A cyclist is travelling along a straight road. She accelerates at a constant rate. Accelerates at a constant rate. That's interesting. As soon as we know it's a constant rate and constant acceleration, our minds should be going, okay, it's either going to be a speed-time graph or it's going to be SUVAT equations that we've got here. She goes from a velocity of 4 meters per second to a velocity of 7.5 meters per second in 40 seconds. So all I want to do before I even read the question is I want to extract that information that I've got there. Ibtiaz, out of these things that I've underlined, are there anything that you can tell me what letter they are represented by? Good, so we know that t is equal to 40. Zishan, what about any of the other values that I've got there? We've just been reading it through together. Why weren't you listening while I was reading it? Faisal?
V equals 7.5.
Yeah, the speed it finishes up at is 7.5 and U is 4. Okay, so we've now got 3 of the values, which is what the question wanted us to have. It said find 3 of them, then you can find a 4th one. The first thing it wants us to do in part A is to find the distance that she travels. It's going to be related to her displacement. So we're trying to find out for part A what the displacement is. It's not very mathematical for me to say S equals question mark, but it just reminds me what's the thing in the question that I'm looking for. The formula that connects those 4 things together, we've only got 2 to choose from, is S equals U plus V over 2 T. So we have 4 plus 7.5 divided by 2 multiplied by 40, and we come up with 230. We just come up with 230, and the units for that would be what, Shahan? Meters. Okay, it's just going to be in meters for that bit. The second thing is going to be the same set of values that we've got. We've still got t, we've still got u, we've still got v, but it says they want to find her acceleration in these 40 seconds. So we're going to try and find out what the acceleration is using these 3 and this one that I've got here. So for part B of the question, the formula that links those together is v equals u plus at. Do you notice how I haven't rearranged the formula? I'm not going to rearrange the formula here. I'm going to substitute in the values and then I'm going to solve the equation. I've seen some people who've been taught to rearrange the equation first. I don't recommend doing that. I recommend putting the numbers in and then solving the equation because we're usually better at doing that than we are at rearranging. Yes?
Can't we use the formula that was first given before? The A equals V minus U over T.
We can do, but what you're going to find eventually, if I just kind of cycle through a couple of slides, you're going to find that these are the formulae that you get provided in the formula book, and these are the ones that if you said to a mathematician, if you ask like an older sibling who does maths, they will tell you these formulae. They won't tell you A equals V minus U over T, okay, just because that's the way that we remember them. But very good question. I mean, you could use it if you remember it, but there's a lot of stuff to remember. So we get 7.5 equals 4 plus AT. Well, I don't know what A is, but I know that T is 40, so I get plus 40A. So I can do 7.5 minus 4 is 40A. So acceleration is whatever that thing is, which is 3.5 divided by 40. Great. Which is 0.0875 meters per second squared, because it's acceleration. If you wanted to, you could round this to two significant figures. So it would be 0.088 meters per second to two significant figures. Really just using the formulae, but what you want to see here is where did those formulae come from? They came from the graph. They came from everything that we've learnt so far. Okay. So things get a little bit more complicated, obviously, and they're not all going to be just using the formula. This one we're going to have to think a bit of some of our logic about what's happening here. It says a particle moves in a straight line from a point A to a point B with constant deceleration, 1.5 meters per second squared. I'm actually just going to pause at that point, and I might even draw something that will help me imagine what is happening, okay? It says it moves in a straight line between A and B. So it's moving in this direction, which I can use with this little arrow here. But it says that it is decelerating. What do you think a deceleration of 1.5, what could I represent a deceleration? As a negative, because it's actually slowing down. So if you wanted to, on your diagram, you could use this double arrow here, and you could say that it's minus 1.5. A double arrow represents acceleration, and a single arrow represents velocity. The way you can remember that is that it's meters per second, and this one is meters per second squared. So there's two of those arrows there. It's just a shorthand way of showing what the acceleration is. The velocity of the particle at A is 8 meters per second. So I could say over here it's 8. You don't have to draw a diagram for this either, but I'm just trying to show you, if I were to draw a diagram, what it might look like. And it then says that the velocity of the particle at B is 2 meters per second. So let's get rid of this. I don't need this arrow anymore. Find the time taken for the particle to move from A to B. So I want to know how long does it take to do that journey that we've got there, and then I want to find out the distance that it takes. The diagram helps us to visualize all those things that are going on. So out of S, U, V, A, and T, Charmaine, are there any of these values here that you think you can tell me what the value of S, U, V, A, or T are? Which of those values is referring to the acceleration? Pardon? No, I don't think you've been listening. I've said this is the acceleration, this is the deceleration. It's actually in the question, so just make sure you're reading through and listening when I'm speaking, okay? So we get that the acceleration is minus 1.5. Oh, well, what about any other values you can see here? Which one, U or V? Which one is U? Which is the initial velocity? Okay, it's 8, and the final velocity is 2, okay? We're going to find the time taken for it to move from A to B. So the thing we're looking for is T, and the equation that links these things together is V equals U plus AT. Substituting those values in, you get 2 equals 8 minus 1.5 T. This is really similar to that part B that we did in the question just now. So we'll rearrange this equation and solve it to find out what T is. So we get 1.5T equals 8 minus 2. So T is 6 divided by 1.5, which is 4 seconds. And that's my part A of the question. And then part B of the question wants us to find out what is S equal to. Well, we know that S is equal to U plus V over 2 T. These are the only two formulae that we're using at the moment. If you do physics, you obviously know more of them. At the moment, we are only going to be using these two. So the distance that it travels will be 8 plus 2 divided by 2 times it by 4, which is 10 divided by 2, which is 5. 5 times 4, which is 20 meters that we've got here. That first part should be straightforward and nice and easy. The second part of the question may be a little bit more complicated. So if you finish writing that down, start reading what it says. Okay, so in this journey, it's gone from 8 to 2 in 4 seconds. You wouldn't necessarily need to do this, but I'm trying to teach you some extra things here, right? What's going to happen after 1 more second? What would the speed be after 1 more second? 0.5, because we're going to decrease this by 1.5. What would the speed be after another second, after it's gone down to 0.5? -1. Okay, so the velocity of it after 2 more seconds is -1. What does that actually mean if its velocity is -1? Yeah, it's traveling. It was traveling like this. It was going from A really fast. It started slowing down. And then it's going to start traveling back. In real life, when we talk about deceleration, you're probably thinking of riding a bike or driving in a car and putting the brakes on. When you put the brakes on in the car, when you stop, you don't start them reversing backwards. But in this scenario, we've said that the deceleration is constant. We're saying every second it's going to go down by 1.5. So it's going in this direction, and then it's actually going to come back on itself. That's what's going to happen in this place here. So we'll still grab out the different values of things that we're talking about here. We're going to say we want to know the velocity of the particle at C. So we can either consider it from B to C, or we can consider it from A to C. Which journey would you prefer? Neither of them make a difference. Should we do A to C? Okay, so from A to C, we're going to try and see what the different values are. So the acceleration is still -1.5. What is the time of the journey from A to C? 6. What is the time of the journey from B to C, by the way? 2, because we already know from A to B is 4 seconds, so from B to C must be 2 seconds. We know what the initial velocity is. What's the initial velocity? 8. And the final velocity is the thing that we are looking for. We're expecting this to be a negative value because of what we've just predicted. So the final velocity equals u plus at. So that is 8 minus 1.5 times 6, which is -1 meters per second. So at C, the particle has started traveling back towards A because its velocity is negative. Now, I'm guessing there's probably some questions about this. What kind of things do you want to know a bit more about? Are there any things you're like, hang on, why this thing here?
Would you have done it from B to C?
Yeah, you could have done it from B to C. I'll do that really quickly, okay? So at B, the acceleration is still -1.5. The time we said is 2 seconds from B to C. What's the initial speed when we're talking about from B to C? Pardon? 2, yeah, because the speed is actually 2, and we're trying to find out what the velocity is. V equals u plus at, so that's 2 minus 1.5 times 2, which is also -1. So you can consider it for different stages of the journey. It doesn't have to be from the beginning to the end. You can do it from either of those sections that we've got there. But we don't need to do it from that because we've already done this. Part D of the question then says, what is the distance from A to C? So A was here, B was somewhere over here. It's now started travelling back, and so C is going to probably be around there. We don't really know exactly where it is. Now, I am not asking how far has it travelled. That is a different question. How far has it travelled is how long this blue line is. What are they asking? They've asked for... So what they're asking for is this. They're asking for just what's the distance between A and C. So we're interested in the displacement, not in the distance that's travelled here. The distance travelled would be harder. You'd have to work out the distance to this stage and then the distance to this stage. But for this one, we just care about the distance between A and C. So the thing I'm interested in is S. I know what U is. When it started at A, it had 8, and now it's at C, it's coming backwards, -1. So we get 8. V is -1, and the time that it took to do the journey from A to C was 6 seconds. So S equals U plus V. Well, V is negative, so it's just going to be -1 over 2 times 6. So that's 3.5 times 6. How much, sorry? 21. So the distance is 21 meters. So actually, my diagram perhaps isn't right. My diagram doesn't seem to be right here. It seems like C is actually still after, okay? It hasn't actually stopped and started turning back yet. It's slowed down, and it's gone beyond B. So really, if I go back to my diagram, if I were to edit this, it looks like C is actually just a little bit on that side. Can you see why it has to be on that side? Because it's gone further away. Instead of it being 20 meters, it's 21 meters. But I wasn't to know that until I'd done that calculation. If the distance between A and C was 18 meters, then C would have had to have been closer to A than B was. So you've got a question that's on the bottom of that page that says your turn. I want you to have a go at doing that question on the bottom of that page, and then we're going to do some questions on the whiteboards, okay?